Chapter 1, Section 8 is talking about the derivative now as a rate of change. So the first example is right in front of you, so read it along with me. Suppose that f of x, which is x squared, and we're asked to calculate the average rate of change of it over certain intervals a, b, and c that are listed below. The average rate of change of this function over those intervals is calculated based off of the average rate of change function formula that we know. So if we take a look at the secant line of x squared, then we can notice between the intervals 1 and 2, we can find those 2 points, they're marked in red and orange, that when we use that average rate of change formula, we find a slope of 3. Well, if we continue to use our secant line in that formula to find the average rate of change, but we make our intervals smaller and closer to one another, and again, it's still the secant line, but notice the interval, then you can notice a change in the average rate of change. And looking at that last example, it's still the secant line, except we are really, really close to each other on this interval C, and then again, our rate of change is also different and smaller. So, a couple of things to note. Notice that the interval in example C is smaller than the interval in either A or B. The sequence of answers from above suggests that as the interval gets smaller and smaller, the average rate of change for this function goes towards the value 2. This concept of shrinking the interval leads us to a conclusion that the instantaneous rate of change at x equals a at a certain number equals the derivative of that function at that number. So I kind of just said it, but down in blue, meaning the instantaneous rate of change of a function equals the value of the derivative of the function at that particular point. Okay, so let's look at an example. So we are moving now from the slope of a secant line, which is the average rate of change, to the slope of the tangent line, which is our instantaneous rate of change. So if you look at example 2, consider the same function x squared. Calculate the rate of change of f of x at 1. So the first thing that I did in this problem is found the derivative of f of x, which we know is 2x, and then I plugged in 1 into the derivative to get a value of 2. So, in other words, the function is changing at a rate of 2 units for every unit change in x. Okay, so that box on the right says that note only one x value was given. We're looking for the instantaneous rate of change, so therefore take the first derivative. So all those things are important when given these problems. So let's look at our own sample problem. Consider the function x to the third. Calculate the average rate of change and then the instantaneous rate of change. So I'm going to add down here, when you see the words average rate of change, you're going to think the slope of the secant line. And the slope of the secant line is just going to be our typical change in y over change of x. So I would write that as, we could say m equals change in y over change of x. There's a whole bunch of different ways that we could write that. So we have the function at 3 minus the input of the function if we inputted 1 over the change in x, which is 3 minus 1. So if I take 3 and 1 and I plug it into f, which is x squared, I'm going to get 27 minus 1 over 3 minus 1, which gives me 26 over 2 which gives me 13. So that is the average rate of change between those two intervals for this function. So now if I wanted the instantaneous rate of change, though, at just one value of x at 2, you are going to think slope of the tangent line. And then the first step you're going to take to find this is to find the derivative of the function. So f prime of x equals, using the power rule, bring down the 3, and we're left with x squared. So therefore, f prime of 2, since we're looking for it at the value of 2, equals 3 times 2 squared. 2 squared is 4 times 3 gives me an instantaneous rate of change of 12 at the x value 2. Okay, position functions, velocity, and acceleration. Another way to think of a derivative is as a rate of change. So the derivative of a position function describes the rate at which the position changes. Can you think of a word from physics that describes the rate at which the position of an object changes? The velocity. All right, so carry this logic to one step further. The rate at which the velocity changes of an object, the velocity of an object changes, refers to the acceleration. All right, and these concepts give us this box down at the bottom here that you must memorize. So if we have a function y equals s of t, and it's a position function, then we can say the first derivative of s of t equals the velocity. And then the second derivative, which is the derivative of the velocity, since that's what the first derivative equaled, is the acceleration. So we have a symbol for velocity. Our velocity is v of t and our acceleration is a of t. Meaning the first derivative of a position is velocity and the derivative of the velocity is acceleration. Again, you must memorize that. All right, so let's close with some examples. So example 3, suppose a baseball is thrown upwards so high, wow, okay, it's late. Sorry, upwards so that its height in feet is given by this function h of t, where t is the time in seconds. Find the velocity of the baseball 2 seconds after it's thrown. So always ask yourself, what are they asking me? Well, we are looking for velocity, therefore we need the first derivative of our given function, which is h. So the solution is down there, done for you. Since velocity is the derivative of the position, the derivative of h equals negative 32t plus 128. So therefore we take our value 2 and we plug it into that function to give us 64 feet per second. All right, so let's do one together now. Find the velocity of a baseball 3 seconds after it's thrown. All right, so very similar question. So once again, what's it asking for? The first derivative. So we're going to, it's the same function, so we don't need to do the derivative again, but I will rewrite it for you just to be clear. So h of t equals negative, why I want this right? Negative 16 t squared plus 128 t plus 5. So therefore, the first derivative of t, which is equal to the velocity of t, equals negative 32 t plus 128. So since that's what we're asking for, the velocity, I'm now going to take 2 and substitute it in for t here. So v of 2 is equal to negative 32. Oh, I'm sorry, 3. Not 2, we just did 2. Okay, so negative 32 times 3 plus 128. And this gives me 32 feet per second. Always make sure you label your answers. All right, and the final part is now it's asking to find time. Well, this is a function in terms of time. So if we're asking for time, we are going to set a function equal to the variable and then solve for it. Well, we need to keep in mind, though, that what they give us, because we only need one unknown, which is t, they give us the velocity. So I worked this problem out for you here to help start along. However, you have to make sure you know what they're asking for. If I want the t when the ball reaches a certain height, then it's just the original function, and we solve for t. If I want time with the velocity, and you haven't found the derivative yet, you're going to have to do that. And if I ask you a question about time in terms of the acceleration, you're going to have to do the same thing, find the second derivative and then solve. So make sure you know what is being asked of you. All right, so we're going to set the velocity function equal to negative 32 and solve for t. So that is the work that you see there. Now take a note of this. A negative velocity implies that the baseball is falling rather than rising. All right, so just keep that in mind since it's set equal to a negative value. So now we're going to find the time when the velocity is 64 feet per second. So we're going to still use that derivative function, now set equal to 64. So the first derivative is negative 32t plus 128. Subtract 128 and we get negative 64. And then after you divide by negative 32, t is going to equal 2 seconds, which we actually already know it would be based on the problems we did prior on the page before. So again, just make note of now what we are calling velocity acceleration in terms of derivatives of functions. Please make sure that you have the velocity and acceleration, those concepts memorized. And then also take a note now that we can consider a derivative now as a rate of change, the instantaneous rate of change.